it's time. Thank you very much for joining this training session. I'm glad to present to you the new I/O format, which we needed last years for OpenFOAM. So this training session is about Coherent I/O format, which I worked during the ExaFOAM project, carried out during the last 3 years. First, it was implemented in Foam Extend, and now that was the training session of the last OpenFOAM workshop. Now we have a new version integrated into the ESI foam V2406, and yeah, let's have a look. The slides are mostly the same as in the last training session, because the Coherent format itself didn't change. It's just the integration which took part, but the live demonstration hands-on session is different. So first, in this presentation, I will talk about the bottlenecks of the current I/O formats. We will have a look at the architecture of the current and the Coherent formats. We will talk about the transport layer, so the backend of the Coherent format, how the data is written to the storage, about the performance, and yeah, I will have a live demonstration experience how to work it with it. So the current legacy formats is ASCII and binary. We call it uncollated. Uncollated means in this case that you have processor directories for each MPI ring, for each partition. And that's the first point. The number of files written scales with the number of cores you run your case with. Once the case is decomposed, if you want to change something, a boundary condition, for example, you need to change it in every file which has this boundary condition. So it's basically n files, and you probably, if you have 1,000 processor directories, you will write a script. It's inefficient, and it can only be restarted on the same number of cores. Substantial amount of time to solution goes into I/O for the decomposition, reconstruction, or redistribution. These problems, we knew about them already. We have them since 10 years. They're quite painful. That's why the collated format was developed. It reduces it solves the largest problem with the number of files. So it reduces the number of files, but it doesn't solve the other issues mentioned here. These issues stay for the collated format as well. There was another effort done by Mark Olesen from ESI called Adios Foam. Basically, what he did, he used Adios tool library to bundle the processor directories into the Adios 2 format. So this code, it's better if you can try it out if you're interested. It's also publicly available. So I have a dream, right? Define your dream. Decrease time to solution. So just imagine, start a parallel run without any pre-processing on desired number of cores. Just at the case you define, want to run on 100 cores, I started. No reconstruction for post-processing. No reconstruct file anymore. If I want to change a boundary condition, I just change a single file, like I do it for a serial simulation on a single core. should be the same for a parallel case as well. When viewing a slice in ParaView, so I just do a slice or clip, then load only the data associated to this slice or clip and do it fast. Lossy and lossless compression, which is now available in open form. It's good to keep it. And sometimes dreams come true. I should admit, not all of them, but we're going into the right direction. So the idea of the Coherent format comes from Henry Krusche, colleague of mine. I think he had this idea since 7 years, and only during the Exaform project he found the funding to develop this. So yeah, as I stated, all the works were done during the Exaform. We did first, since we have expertise, more expertise in form extent, we did the implementation there. And basically there were two partners, HLRS from Stuttgart, it's a supercomputer center, with Gregor Weiss, Andreas Ruop, and Flavio Galeazzo. And from our side, it was me and Henrik as well. Then later, at the latest part of the Exaform, we integrated it into the open form V version, the ESI version, and it has been published yesterday. So I got an email from Andrew Heather that they made it publicly available. So let's look at the current format. How does it look like in serial at first? I have a quite simple mesh here consisting of 6 cells, 0, 1, 2, 3, 4. These are the black numbers. Then we have faces. Faces are red, and they begin first. The internal faces are first the internal faces are numbered, then the boundary faces. So it's 0, 1, 2, 3, 4, 5, and then the boundary faces are coming just at the end after the internal faces. For points, there is no particular order. Points are green here, but there is no scheme behind it, or no, at least no obvious scheme. So, and that's how you write it down. Yeah, for phase number 0, we have so that's a connectivity pattern, right? You need somehow to bring connectivity to the storage to know how to build your mesh. And that is done in this way. We have a list of faces here. So we've got 16 faces in total. And first, the internal faces come. There are only 7 of them, from 0 to 6. And the connectivity is done by owner and neighbor, where owner of the face is the cell number, which owns this face, right? So, and the neighbor is the cell which is neighboring this face from the other side, right? So there are only 2 counterparts, owner, and neighbor. And that's how it goes. So the first 3 faces, 0, 1, 2, are owned by cell number 0. And they have neighbors. The 0, 1 has neighbor 1. The first one is neighbor cell 3 and 5 here. Okay, how does it look in parallel? So first of all, we need some decomposition algorithm, which will order the cells based on some algorithm. some heuristic. And then what we have here, the faces and points are duplicated at processor boundaries. And actually, that's the case both for memory and the storage. So they are quite actually identical, how it runs in the solver and how it's stored on the system. And as you can see here, we get the processor boundary here. And we need to save these points. This point is actually the same point as this one. This point is the same point as this one, is 0.6. We have to save them twice. So that's a processor 0 directory. That's a processor 1 directory. They will be duplicated. And yeah, you can see it here. So these are these duplications, right? So we need somehow to come up with a new format, which first of all solves this duplication problem. Because if we want somehow extract the slices out of it, we don't need this duplicated data. What we do, yeah, so it basically that's how it comes to the name Coherent, because it's coherent in itself, right? Another way to put it, make it sliceable. First of the problem we had is the faces list, right? So here we have it for the example of 2D now. It is here list of lists. In this example, it's of the same size, but imagine you have some tets and hexahedra and other polyhedra. These lists will be of different size. So here 2, for example, here 3, 4, and so on. But we need enable a random access for the list. If we have list of lists, we cannot jump randomly. We need then a second array which identifies how large are our faces, right? So that was one problem. Other problem was the boundary faces are stored at the end of the face list. So I have a first partition here. If I get it sliced out somehow, cut out, I get only internal faces. But all the boundary faces are somewhere in the list down below, and I need somehow to read this from the backwards or do some strange stuff to get. I need to get this faces somehow. So what we did, the boundary faces come always first for each cell, and they got a minus sign before the index. Right. So you can see it. That's for the boundaries. The neighbor is responsible now. So I have it here. Here we had the neighbor only for the internal faces, right? We didn't have neighbors for the boundaries because there are no neighbors. It's a boundary. Now we still don't have neighbors, but we encode the information of the patch into this neighbor array. So, for example, here -1 is the first patch. It's a first boundary. -2 is a face. So face 13 belongs to the second boundary, and so on. And all the positive numbers are still there, so they somewhat have this bring the same information as here, right? The first phase is the first the first phase neighbor is the first cell. That's how you read it. Okay. So that's how if you do the same for the doesn't work anymore. If you do it for the coherent format, draw the same diagrams, you will have representation like this. Okay, so here the names are not quite up to date. I didn't change this, but we changed the names for the integration part, but the sense is the same. Now we need, since the coherent format has slices, and from outside the most important thing, it looks serial. So you don't have processor directories anymore. If looking at the case and listing all the files, you wouldn't know whether it's a parallel case or a serial case, right? So but we need to store this information somehow, because we still need some kind of decomposition, and it's stored here in partition starts array or partition offsets. Then we have the owner array, and the nice thing about it is now everything is consecutive, and we just need to provide an offsets for the owners. So this owner start, or in other words, owner offset, means that for the cell 0, the faces I own start at 0 and end at 4. So I own 0, 1, 2, 3, and 4, the face numbered like this, and so on. For cell number 1, it's from 4. These are the faces 4, 5, 6, and 7. Okay, the face name bar implementation. Now you've got this with the colors, right? So you've got a patch here, B1. It's a blue one. It's encoded with -2, and the purple one is encoded with -1. And the points also got some order. We didn't change much, but they are now ordered with the faces. So basically, phase 0 has the points 0 and 1. Phase 1 has an additional point 2, and so on, right? So you can slice the points as well. So by now, for the serial case, it might have some advantages, this format, but maybe not so much. But when you do it in parallel, that's really great, because now we don't have any duplication information. We can put everything in a single array, right? We can put one array from the 0 processor, then put the next one just behind it, and this is the truth for all the arrays presented here. And to get our decomposition to the ranks, we just drew this line. right? We can find out from the partition offset. So partition offset tells me the partition number 0. You don't see the mouse actually. Okay. Let me change it to. Let me change to this view. Then you will see the mouse at least. Yeah. Okay, so for the partition 0, you start with the cell number 0 and end with the cell number 3, right? So, okay, I know I have to read you can see it. That's okay, thank you. And for the, so I need to read the first three cells, right? 0, 1, 2. Then I know my owner start or owner offset. It's up to 10. I need to read up to 10. So here I go. I read the faces up to 10. Yeah, and so on. So, oops. So that's the basic structure of the current format. I think it will get a bit clearer if we in the live demonstration, if we work with it. So let's talk about the transport layer. Now we talked about the structure, which is very important, but we also need to bring this structure to the storage somehow. The tasks of the transport layer is so aggregation and distribution of data arrays doing write and read to and from storage. Also metadata management. So if it's some binary package where are my arrays, what's the name of the arrays, and so on. And what we chose is Adios2 because of following reasons. It's designed for HPC. It also allows partial selection for global array. For example, for MPI rank. It enables lossy and lossless compression. It's also simple. It was simple to set up and to use and to integrate for us. You, as a user, you also may configure it according to your needs. There are other transport layers. For example, the MPI-IO represented here. I think I won't go into the details, but the thing why we didn't choose the MPI-IO was because we needed to do more work on the management. So we needed to implement the management of our files, right? So the names, how the data is stored, some database maybe. We just skipped it using Adios2 functionality. Okay, and here are some benchmarks. I showed, if you're interested, of the benchmarks in a particular case. For example, for Grand Challenge of Hexaform, it's a combustor case. You can look at my presentation from yesterday in recording, or if you attended it, you saw it. So it's for pre and post processing. It's really good, and the write performance was comparable to the collated format. Here, at the beginning we did some benchmarks just to look at how the transport layers perform without the solver. actually. So basically profiling the transport layer performance. And what we did here, we write it 64 kilobytes per core, which is actually 8,000 cells per core. So that's one of the best performing points for the Combustor Grand Challenge. We used profiling tool named Darshan to measure the I/O performance. And on the right-hand side, you can see the results. And on the x-axis, that's the number of nodes. And the I/O performance measured in maybe bits per second is on the y-axis. And as you can see here, there is POSIX. So POSIX is basically uncollated format, the legacy format in binary. And you see this huge spread, right? And the median, so this gray gray lines, it's quite low, and the spread is big because the load to the system is quite high, right? For one node, it's already, the spread is quite high for one node. And you see when you use 264 nodes, a lot of processors, yeah, it's quite low. So comparing the MPI I/O, there are also some levels. Level 0 is non-blocking I/O. Level 3 is the collective blocking I/O. And the blocking in this case, level 3, showed better performance. But the key message here, the Adios 2, the green one, is on par with the MPI I/O. So we were satisfied with this, with our choice, and that's also the reason why we chose Adios 2. Okay, so now we come to live demonstration, and as I mentioned earlier, there is now the Coherent I/O format is integrated in OpenFOAM V2406. I think it was published yesterday. At least this repository was published yesterday, and it's not now in the release version. So if you download the official release of OpenFOAM, the Coherent I/O form won't be there, because we want first to get it to the public for you to try it out. We didn't test it so much. I tested on my cases. I still see some issues. Not everything is working, right? So basically, we began only with the geometric fields. Post-processing is not there. Peer review is unfortunately not available yet, so you cannot load it in peer review. And Lagrangian, this stuff is not yet implemented. So we began with geometric fields. But what the good news for this, it's different now as a year before. Now we can mix the formats. So you can use the Coherent format for geometric fields. And if you have some additional data for post-processing, some functions, function objects, you can use collated format for this, for example, or for whatever, right? Okay, so yeah, let's have, I think I don't have internet here. Try, oh no, it doesn't matter, but if you, maybe I have it open here. Ah yeah, I have the wiki open. So you need to be a little bit careful about this, because you need a particular branch. If you land on this I/O page, the master branch is actually the master of the open form version. You need to choose this one, Coherent preview .v2406. And why it's like this? It's explained on this wiki page. So look at the wiki page mentioned here below. It's because it's rolling branches. So it means we need to integrate some things into the core of the OpenFOAM, and it's better if we do it in the development branch of OpenFOAM. But we don't want to have Coherent IO in the release repository of OpenFOAM, right? So that's why it's these branches are always rebased on the developed branch, where the new features come into the core needed for Coherent format, and then everything is applied on top of it regarding the Coherent format. Okay. Are there any questions so far?
It seems the Coherent preview branch is still the official platform on that.
It's publicly available, right? So you can access it.
Yeah.
Yeah.
Coherent preview branch.
The current preview branch. Yeah, that's.
It's still the official.
It's an official repository, but what I meant, it's not in the main repository. There are now so it's a GitLab.com. They moved almost everything to the GitLab.com, so they now there are many repositories there. The official one, the release one, is not this one. This one is the official one is somewhere under OpenFOAM, and this one is, if you look here, it's in community exaFOAM IOR, and then there is a branch. So
yeah, that branch
is public.
Yeah, but it shows the code of official OpenFOAM. No.
Yeah, that's that's how it should be. Yeah, definitely. You're welcome. As I said, you're welcome to try it out. And even more, I will show you how to do it. Yeah.
I'm too confused about this Coherent IO. My understanding is when you compose the domain, for each subdomain, the indexes are just continuous, consecutively indexed, right?
Right.
I mean, the first subdomain, say, if it is indexed from 1 to 100, and then next one is 101 to 200. Only this.
Exactly. Yeah, if you put if you want to shorten the message, that's what make it so good. It's like it's sliceable, right? So you have consecutive arrays, and you can slice at any point. That was not possible before, right? So for in every processor directory before, you started from 0, right? For every index, and you had this duplication, and you couldn't slice it. So there's many issues we had to overcome.
Thankfully getting my time. So is there any problem?
Try it out. I don't know. I can tell you I haven't tried. I suppose there will be problems because cyclic AMI needs additional fields. Maybe not. You're welcome to try it out. I actually some days ago I tried some new things and I was amazed that worked. I haven't inspected it, so you have to try it out. Okay, let's start with the live demo. Kein Problem. To the presentation. Uh, 10, okay.
But we found that the first zero, but never is a -1.
Say again? What is it? Phase 0?
Yeah.
Phase 0 is here.
Yeah.
You mean the neighbor?
Yeah.
But there is no neighbor 0. 0 is only the owner. It's the first one, and it only owns. It never acts as a neighbor. You know, I mean, it owns all the faces it's connected to. It owns 0, 1, 2, and 8. No, okay, 8. You wait a second. The 8 is boundary. Sorry, phase 0.
Phase 0 is the boundary on the right.
Ah, okay. I remember this problem from. Okay. Yeah. It's.
You mean when you highlight the numbers with the yellow color, then it is just the boundary.
So, wait a second.
Look at the image on the right.
Look.
This one to the right. After you divide it too far. No. More to the
Here.
Here. So here you have the 0 where phase 0 is the boundary, which corresponds to the table.
Ah, you're talking about this one. Mm. I have to say that these two do not coincide actually. Okay, but the serial mesh. So where is your problem? Your problem is in here, or is it in here?
Neighborhood face and neighbor. Face 0 and neighbor is -1.
It's -1. So if you look here at this one, I didn't check the numbers here. I was looking always. I think it's the wrong one. It's the wrong one. It should be actually all the same, right? So please don't look at the partitioned one. Look at the serial one, because the serial is the same as the partition. And if you look here, we start first with the boundaries. And the boundary here is the first boundary. It's it's B0 in this case, and that's encoded as -1. The first boundary is minus and the index of the boundary. It's a second boundary. Okay. Are there more questions? Okay, let's start for the demo. With the demo, we're quite advanced in the time. Okay, so I have here side by side. Oh, wait a second. Keep my notes out. One case is set up for the coherent, so it's a cavity case. I just you can copy it from the tutorials, and the only changes what you need to introduce is in constant control dict. Oh, constant. In system control dict. You need to put the right format to coherent. Okay, so it's always ASCII here or binary, right? So now it's the coherent one, and then also for the fields here in the 0 directory, for example, the pressure field, it needs to mention that it is in coherent format. But all the internals may stay the same as before, right? So we still can, if there is no data inside, if the fields are uniform or only provide some boundary condition like 0 gradient, that stays the same. Okay. So that's what you need to start going. And let's build the mesh. I just check what's the setup for the mesh in block mesh dict. I think let's reduce it by now to some smaller count, like 4 cells. It's easier to comprehend. And let's run block mesh dict here. And on the right hand side, I have the cavity in ASCII format. Let us check. So that's the pressure field in the 0 directory. It says ASCII here in the header. And let's look here. Oh, it's already 4 cells as well. And in the control dict, the right format is ASCII as well, right, as you can see here. Okay. So let's run block mesh here as well, right? So the output is identical, but let's look how does the polymesh looks here for the ASCII, and how does it look for the coherent format. It's quite different. So in the ASCII format, as I mentioned, that's the structure which I presented in the slides. We have maybe we can view it side by side. Let me do the coherent first. So in the Coherent format, we have only somewhat two files. It's one file, and other file is this data BP file, which is actually a directory, but the DOS2 guys call it a file. If you look inside, go into the directory. So there are some files there. It's binary files, indexing, some profiling in JSON. So it's their format, right? Okay, and let's look in this Coherent format. Coherent file. It's an ASCII file, so you can read it. It just basically for an overview. So this first information is not used for reading, and you can see here it's number of partitions, number of cells, number of faces, and boundary faces for the complete case, independently if it's serial or parallel. The important part, which needs to be here and which we read, is the boundary. So the boundary definition happens here for the polymesh, and we have three boundaries here, as you can see. So cavity case, moving wall, fixed walls, and front and back. Okay, what do you do with this data BP? It's a DOS2 format, and what you need is the tool called BPLS. And if you download this OpenFOAM branch with the Coherent IO format, you will also need the DOS2. It's already set up. You just need to put the DOS2 in the right place in the third party directory, right? And it will be compiled as well if you compile OpenFOAM. And the third party is discovered by OpenFOAM. And then you will have this tool available. It's called BPLS, so BP list, like the list tool for the BP format. Let's run it on the data BP. And what we get here are our arrays. As I said, the names are a bit different than I showed before, but you can recognize already the points, right? We've got 18 points. These are vectors of 3 elements. There are partition offsets, owner offsets, neighbor, face arrays, and boundary arrays. So let's have a look at this one for how do you read particular array. You write BPLS data BP minus D, and then you choose the one you want to look at, for example, the points, and you get the points here. Be careful because at DOS2 there are some conventions how it prints the data, but it prints just one after another, right? So actually this is the first point, that's the second point, and basically the second vector. But you can recognize how it's structured from this tuple. So it begins with 0 vector and 0 element. Then it continues on the next line with the second vector and 0 element. So that's the beginning of the second vector, and that's the 0th element. But we can print it in a more pleasant manner by defining the columns to 3. That should be sufficient. Now we got our 18 points, right? Represented nicely. Okay, so not much change to the points, right? So if let's do it here. Let's print the points here on this side. I need to change. Now the order has changed, as you can see. The first point is not the same, but yeah, points are points. Okay, let's go further and check the partition offsets, which identify our partitions. Okay, so we have only one partition. It ends with a it begins with a 0 cell and ends with a third one, but we for reasons in to enable easy for loops, we just save here n+1. So yeah, it's 3 + 1, right? There are 4 cells in this case. And yeah, and so on for the owner F offsets. No, that was no. Right, so here's the identification of the faces, right? And I can see how the faces are structured from this array. And yeah, so okay, you need some connection between the face offsets, because these are the indexes of the from this array, from the face points, right? You remember we needed to flatten the arrays. That's why for the faces we need this tool, because the faces are not always consisting of the same number of points, right? So we need to index which points belong where. And that's why we have an additional array. It identifies, it maps somewhat this array, so the face offsets array to the points array, right? So for example, my face number 1 goes from 0 to 4, and these are the points I have to get my face, right? 0, 1, 2, 3. I go into the points array and get the points 0, 1, 2, 3. These are the points of my face. Okay, so we looked a bit inside. Do you want to, yeah, just maybe show the boundary that this file is quite similar to this one. Start face is actually also the same. Yeah. So let's run the case. I just start icoform. Okay. And I get my time steps. If I look into them, I see the following picture. Let's go in the 0.50. So we tried for the fields. We tried to make it, we made it user-friendly as possible. We kept the ASCII files there, and these ASCII files you can edit them. So you can go into the pressure file, right? And you can still, it's still editable. It's not a binary file. Let's do the same here, actually. On the ASCII side, I just run icoform here. And I go into the 0.1 directory. I've got also these ASCII files, but they look a bit different if I go inside, right? I have here, for the internal field, I have this non-uniform list scalar and then the field itself, right? So it's 4 cells, and I have 4 values here. That's quite different in the coherent format. I've got a name and the total number of this array, and there won't be any information in the ASCII file. So all the data regarding the field, it's not present here. There is only metadata. This name is very important. So remember this, it's P internal field. And if you look into the, with BPLS, you can see there is a data BP here, which is actually not present in this case. So that's coming from the adios 2 and from our integration. If you look inside, you will find P internal field as well. So all the data is stored here, and but the names of the data are in the ASCII files. And we can view how does it look like. No, should be the same probably. Yeah, perfect agreement. That's amazing. Okay, so that's how it looks like for the fields. The same maybe just for the vector field. It's U internal field. Okay, and that's the internal field. Again, we can for the U, for the velocity vector, we can do it with the columns, and now we get the velocity vectors. Okay, amazing. So that's the serial part. Let's dive into the parallel one. And first of all, let me increase the size of the problem in block mesh dict. Let's take somewhat 20. Let's clean the case, run block mesh again, and run it in parallel. Maybe first, wait a second. Let me do it the same thing here. I don't have all clean here. Okay. Twenty block mesh. So that's the ASCII case. And if I do MPI run minus NP2, icoform parallel, then I'll get a problem. Okay, it's complaining about also decomposed predict, I think. Let me check what's the decomposed predict is mentioning. Okay, here it's 2 domains. Let's make it 2 as well. Maybe change this one 2. Yeah, it cannot find the file because we need to decompose it before, right? It's still serial. Let's try it with the Coherent format. Microform parallel. Oops, some misspelling, sorry. Parallel. And it works. We didn't do any decomposition, right? That's a great stuff, but I need to say there is one but here. It runs, but it may be pretty inefficient because how it divides into the partitions is it uses the numbering from the block mesh. How block mesh built the mesh, it numbers somehow my case, and I just slice it after some part, right? So that's that might be inefficient if my numbering coming from the mesher is quite random. Then I get random partitions, and they are far away from each other, and I have a lot of processor boundaries that might be quite inefficient. Yeah.
Here we do not need to compose.
That's what I'm saying. You don't need it, but you should. You should decompose. But it might be inefficient. It might be very slow. We have a cavity case here. You won't see it how slow it is because it's 20 by 20 cells, right? But if you go to 1 million cells, you will see and 1,000 cores. It might be get very inefficient, very slow, right? So in general speaking, you need to decompose, and decomposing in this case we put it in other utility. It's called renumber mesh. Maybe you're familiar with it. So how do you decompose the case? Renumber mesh, I use this one a lot. Renumber mesh minus help minus full, right? And I get this help here, and there are new options here. So for example, there is an option decompose. And let's use it. We use the decompose option. We also can now say that the renumber method is none, because renumber mesh was actually built to renumber the mesh to make it more efficient to run. And never mind. Let's just decompose it, and let's look at our. It wrote. Okay. Let me override the mesh. Because without override, it will put the mesh into the first directory, into the first time step, right? You see the polymesh here. We can look into this one. So I just go here into data BP. No, wait, it's data BP is empty. We need to go to polymesh data BP. And as you can see, the partition offsets has changed. So now we have 3. And if we look inside, so there are 2 partitions now. The first partition starts from 0 and 200. The second one starts at 200 and at 400. And we can change it in decompose pardict. So decompose pardict is still red for this option. If we change it to 4, oh, it's Scotch. We don't need to change the coefs. And we renumber again. Let's do not override. Let's put it in this time step, and we will look at the partition offsets again. There are now 4 partitions: 0 to 100, 100 to 200, and so on. Everything is changed. Everything. So the decomposition algorithm orders the cells, and everything is propagated into the rest. Yeah, the BP file. Yeah. So that's what I showed. There is an option. If you don't provide this option with override to renumber mesh, then it will write it into the first this time step, the first time step, right? Let's just block mesh first. I just cleaned it, right? There is nothing here. I run renumber mesh with the decompose. There is this first time step, and here is the new mesh. If I wanted to go to the constant polymesh, I provide override. Sorry, block mesh again. I provide override, and then there is no time step here, but I have it in the constant polymesh data BP. You see partition offsets is of size 5, so there are 4 partitions. Okay, it's we're almost out of time. What I would show you more. Yeah, and the great thing, no reconstruct par is needed, right? So you don't have it's still like a serial case. I will just run it with MPI run on, let's say, on 2 partitions. Doesn't matter, right? If it's decomposed in 4, well, with the coherent format. And if you look here, still everything looks like it's serial, right? And you can look into this data. It looks also serial. You maybe, I think there is this one, D, where can you see the blocks, how the blocks are written to the storage. So it's internal of Adios, but there you can imagine, okay, there were more ranks working with this arrays, but that's not so important. Okay, maybe one last thing I want to show you for the how do you identify how the case is decomposed, because now it's not so easy. Renumber mesh has this opportunity to dry run. Another option is write maps. And let's do decompose. I think that should be enough. And then if I use these two options, dry run and write maps, I get a VTK file, which I can view with ParaView. No. And there I have a field named ProcID, and I see how the cells are split here, right? Yeah. So if I don't provide renumber method known, it still renumbers the mesh on top. It renumbers. It sees that you decomposed, and it renumbers each partition. Okay, we're out of time, so I have another case. Try it on your own. I just tried it out yesterday. The elbow case, also an incompressible case. It has some, it has some other utilities like fluent mesh to foam, and I wouldn't expect that it works right away, but it worked in my case. So no, you see, I got the results from just by running the all run scripts. So I think we stop here. If you have further questions, I will give now the opportunity to the next speaker, right? Just talk to me outside. I'm open to your questions, right? Thank you very much.